Welcome to Physics World. Every day in the morning, you hear so many sounds. Some sounds are pleasant to you. Some sounds are noiseful to you. But anyway, even they're pleasant or noise, you're hearing the sound. And you produce sound also while you speak, while you talk to a person, while you move a what do you say that a heavy body on the surface because of friction. If you take a chalk piece and if you write something on the board with a chalk piece, it produces sound. When you switch on the audio player, it produces sound. TV produces sound. So sound is everywhere. So you have to learn how to listen to sound, how to control the sound. First point. Second thing, how do we communicate with each other? You may know, you may have heard, or you may learn in English classes about two types of communication: verbal communication and non-verbal communication. And the difference is, verbal means by speaking, unwritten communication, oral communication, how at present how I am communicating to you. Non-verbal, without talking, written, by writing, by using some signs, some symbols. If you communicate to other person, it's called non-verbal communication. But 80% all we do verbal communication only, means we speak and we talk, and there we produce sound. Now here it is very, very important that what is the physics behind sound? How can we produce different types of sounds? How can we control the sound? And how the human being, how we are producing sound? Do you have any other machine inside which is producing sound to us? Or do you have any other machine in your body which takes the sound and makes us to understand? So all these things we need to understand. So that's why, so today's chapter is sound. So if you go to the open theaters, you can see big loudspeaker and it produces a very large sound, so that wherever you are there in 360 degrees, you can hear the sound. Similarly, using mics, when you speak, it produces sound. At present, I am using caller mic, it also producing sound, and you are hearing to me. So all these examples tells you that sound we are producing. And the question comes that what is sound? Sound is an energy content. Yes, it's energy content. How? The kinetic energy is energy. How? The potential energy is energy. Solar energy is energy. Sound is also an energy. Just like light is an energy. When you speak something at one point and the sound is traveled to some distance, say you started speaking here, okay, you started speaking and the sound travels to a point B where there is a person who is receiving the sound. Now, generally, if you want to draw a diagram, we draw the diagram like this. The sound is going from one point to the other point in this direction. What is symbols called? These semicircles are called. It is called waveform. Waveform. Initially, I have informed you that sound is an energy. It is an energy. Now I am saying that sound is a waveform. What is this? Means sound is energy as well as wave? Yes, you are correct. Sound is energy and sound is wave. How? See, I will tell you how it is possible. Scientists wanted to explain to all the people that how the sound looks, because you can't see the sound. You can just experience the sound. They understand that with the sound you can break a glass. With the sound you can move a body. How it is possible? A sound can break a glass? A sound can move a body? It is only possible if the sound has energy. And many examples in the movies, in your TV channels, you have seen that the sound is breaking the glass. And that simple example tells you that sound is energy content. So sound is energy. Now the question comes, how do you show that energy on the board? How do you show that? How do you experience that energy? So that's why scientists made a pictorial representation. And that pictorial representation of energy is called waveform. So wave is the pictorial representation of energy. So it is pictorial, means picture. Pictorial representation of energy. So you understand. So sound is wave because a pictorial representation of energy. But what wave we can use? In mathematics, we have so many types of waves. But based on the changes in the energy, the physicists understood that wave is in sinusoidal form. Sinusoidal form. Sinusoidal form means it is either this way or it is in this way. If you see, both waves look same, but the starting is different. Here the wave started at the origin, O. Here the wave doesn't start at the origin, it started at some fixed value. So either the way you can show the pictorial representation of the energy, which is you can show the sound. So how can we show? Now we're going to discuss. Before going to discuss about the properties and the characteristics of sound, as I mentioned you earlier, sound is a wave. So let us discuss about some fundamentals of wave. Then we go to sound. See here, as I mentioned you, wave is pictorial representation of energy. Now this wave is classified into many types. Mechanical wave, electromagnetic wave, matter wave, many classifications are there. But here our subject is limited to mechanical and electromagnetic, and we are not touching electromagnetic because this is not in sound. So coming to mechanical wave. Mechanical wave means the wave is produced because of mechanical force. That mechanical force is applied because of your muscular force, some machinery force. So based on the mechanical force, the mechanical energy is produced, and because of mechanical energy you have mechanical wave. And this mechanical wave again classified into two types: longitudinal wave and transverse wave. So this is our point of discussion: longitudinal wave and transverse waves. Now the question is, what is longitudinal and what is transverse? See here, longitudinal wave. If you see on the board, I had drawn some dots, some lines. Think that this line is air medium. So air medium or any gaseous medium you can take. For example, I have taken air medium. Air medium consists of many particles because medium is nothing but consists of particles. So as this air medium, you have air particles everywhere. So in that I have chosen 4 air particles, A, B, C, D. 4 air particles I have chosen. Now, when some wave comes through the air, see what happens. So this is how the wave comes. Seeing here, this is the wave is going in this direction towards right side. When the wave goes towards right side, actually what happens, while the wave enters into the air medium, this particle do not stay at rest state. They starts vibrating. Vibrating means to and fro motion. How they vibrate? When the wave enters into the medium like air, the particles will vibrate like this, horizontally. See, I'm keeping 2 arrows, left and right arrow. This means if this marker is a particle A, then the particle A vibrates like this. Like this. It vibrates like this. Okay. Now particle B also vibrates. But how particle B vibrates? When particle A vibrates, this particle A at one point of time, it touches particle B. Immediately particle B starts vibrating. when the particle B starts vibrating, at one point of time it touches C, and particle C also starts vibrating. In this way, all the particles vibrate horizontally. This is a horizontal line. You know in mathematics, this is horizontal, this is vertical. So horizontally. So particles are vibrating horizontally. Wave is also going horizontally. So I can say longitudinal wave is the wave when the particles vibrates along the direction of the wave. So particles are vibrating along the direction of the wave is what called longitudinal wave. Understand? Now examples of longitudinal wave are sound is longitudinal wave. Next, spring, waves in spring is also longitudinal. And you can produce water waves, also longitudinal. So sound, springs, water are longitudinal waves. Now coming to transverse. Now see this diagram carefully. Similar. Air medium, ABCD particles. Now again the wave is propagating or moving in right hand direction. Now this time the particles vibrate. See carefully how they are vibrating. They are vibrating not horizontally, they are vibrating perpendicularly or vertically. Vertical vibration. See. So all these particles are vibrating vertically, but the wave is moving horizontally. That means the angle between the wave direction and particle vibration is 90 degrees. So we say that when the wave propagates in the medium such that the particles vibrate perpendicular to the wave direction, then it is called transverse wave. And examples are light is a transverse wave, light is transverse wave, and waves in strings, string, cord, ropes, all are transverse waves. Of course, you can produce transverse waves in water also. See, water is basically in a different special medium where you can produce longitudinal as well as transverse. So, what we understand that sound is a longitudinal wave. In the sound, when the sound wave propagates, the particles in the medium vibrates in the direction of the wave. Now, let's discuss deep of the sound concept and its wave nature. So we learned that sound is a longitudinal wave. Now see what happens here. This is a cylinder. The cylinder is having a piston and the cylinder is filled with gas. Some gas. You can take air also an example. Now what all these lines represents? Think that each line is a gas layer. Gas actually is nothing but it's a type of air. But how can you imagine geometrically a gas? So in mathematics what we do, either we say this is gas particles, or we can say these are gas layers, right? Or sometimes we can say like this also, gas planes, for visualization of the gas. So here what I have visualized that each line is a gas layer. So many gas layers are there in the cylinder. Okay. The piston is the rest state. This is the state of the gas, its initial state. Now what you have done, you hold the piston and you applied force inside the cylinder. Once you apply the force inside the cylinder, there is a disturbance happens in the layers. How they happen? Some layers are getting closer, some layers are move away from each other, again getting closer, moving away from each other. So this type of structure happens. But if you see, all the layers, many layers are occupied in this volume. Same volume you can take here. In the same volume you have less number of layers. Same volume again more number of layers. Same volume again less number of layers. So the gas layers are arranged such that in the same volume, in some volume many layers are there, in some volume less layers are there. Or in other words I can say, in some volume you have more number of gas layers, more amount of pressure. Yes, because of high pressure all layers are closed. Because of less pressure, less number of layers. Or I can say, because more number of layers are there, it has more density. It has less number of layers, so it has less density. Okay. So, the region which is having high pressure or high density is called compression, represented by the letter C. The region which is having less pressure, less density is called rarefaction. Now see in this diagram, compression, rarefaction are arranged alternatively. Okay, so let me write here, C is called compression. In the name itself tells you pressure. So it is nothing but region having high pressure, or you can say region having high density. High density. Now R is nothing but rarefaction. Rarefaction. This is nothing but region having low pressure, or else region having low density. So this is a definition of compression and rarefaction. And if you see this once again, this diagram, compression and rarefaction are arranged alternatively. So this is how a sound is produced, or sound is traveled in the medium. So by this statement, you need to confirm that sound requires medium. When I started sound chapter, I've been telling that sound in the air, sound in the gas. Sound doesn't travel in vacuum. It requires medium. Okay, come back to this concept. So compression, rarefaction arranged alternatively. Okay, this is good, but how do we show graphically? Or how do we show in waveform? I told you, waveform can be shown either in that sinusoidal form. I have shown earlier the two diagrams. So how can we show? So let me show you here. Take the x and y coordinating system. See, x and y coordinating system. Okay, so y-axis, either you can take pressure or density. You can take pressure or density, y-axis. Now, x-axis you can take time t. Now see what happens. Here you have compression, means high pressure. Let us say this is high pressure, P naught. Rarefaction minus P naught, less pressure. Minus P naught means less pressure. Y-axis I have taken pressure and density. X-axis I have taken time. Now see what happens. Compression is high pressure. So let us take P naught is the high pressure and minus P naught is the low pressure. Now compression you represent in this way. See, peak, the peak, maximum peak, P naught, compression. This is compression. Now rarefaction, low pressure. So that means you go in this way. So this is less pressure. So the curves down, low peak. Now again you get compression. See, high pressure. Again you draw, you get rarefaction, low pressure. So that's how the wave generated. This is the true and real wave generated. If you using instrument, if you see also you get the same type of wave. Actually this is called sine wave. So that's how you can represent in terms of compression refractions, or you can represent in terms of a waveform. So I can represent this is compression, this is rarefaction, this is compression, this is rarefaction. So we learned about the wave nature of sound, and you understood that sound is a wave. It's a longitudinal wave, and it is a collection of compressions and rarefactions alternatively. We need to discuss about the mathematics of the compressions and rarefactions. Before going to that, let us learn sound requires medium. As I mentioned earlier, sound doesn't travel in the vacuum. But how can we tell? How can we prove? So to prove that, let us take a small experiment. It's a jar. Jar is filled with air, and inside the jar you have an electric bell connected to electric circuit. One side of the jar is connected to a suction pump. Suction pump, what is the functionality of suction pump? This pump sucks the air. takes the air from the jar to outside. Okay. Now the suction pump is not working, and when the electric circuit is switched on, then the bell starts ringing, and you can hear the sound also, the electric bell sound. Now the second step, what we do, using suction pump, we slowly sucks the air inside the jar. Then if you observe carefully, what happens, the intensity of the sound decreases gradually, decreases. At one point of time, you stop hearing. But don't think that electric bell is stopped. No, I did not switch off the electric bell. Electric bell is on, electric circuit is on, bell is ringing, you can see the vibration of the bell. Still, you can't hear. This is because there is no air in the jar. So the simple experiment tells you that sound requires medium. Okay, now coming to the different mediums. Generally, we have three types of mediums: solid medium, liquid medium, gaseous medium. Gas means air or any other gas you can take. Liquid means water, milk, kerosene, anything. Solid, wood, plastic, etc. Now the question is, sound, in which medium it travels faster? Of course, it travels in all the mediums, solids, liquids and gas. But which medium travels faster? Okay, to explain this, before explaining this, let me give you some values of the speed of sound in the three mediums. Okay, now if you take gas, in gas, example air, in air, speed of sound, we represent speed with the symbol V. Speed of sound is 330 meters per second. Some textbooks shows V equal to 340 meters per second also. How it is possible? Of course, sometimes we use 330 meters per second, sometimes we use 340 meters per second. It is based on the temperature. When the temperature increases, speed of sound also increases. In general, we take speed of sound in air is 330 meters per second. Now coming to liquid. In liquid, take the example water. In water, around, I'm not telling the exact value, nobody knows the exact value. We will take the average values. So around, the value is 1500 meters per second. See the speed of sound increase in water. It's a surprising thing. We think that speed of sound is greater in air. Now how I'm speaking in the room. I'm speaking in the room and speaking in the air. So my speed of sound is greater, we feel. No. In water, it is speed of sound is faster than air. Now one more surprising thing for you. In solids, for example, take steel. The speed of sound is 5000 meters per second. 5000 in 1 second travels 5000 meters. See how fast it is. So if you see the order, you can understand that in solid the speed of sound is greater than liquid, is greater than gas. So why in solids speed of sound is greater, not in gas? Think about the molecular structure of solids, liquids and gas. Going back to chemistry concepts. In solids, if you see, all the molecules are closely packed like this. They are very closely packed. In liquids, the molecule structure, if you see, the molecules are little far from each other. But in gas, the molecules are in random motion. The distance between them is very large. They fly in different directions. So, as I told you earlier, sound is produced because of vibration of the particles. Vibration of the particles, movement of the particles. If you see the sound, all the particles are closely packed. If one particle starts vibrating, it is very easy to carry the vibration all the particles because very close. So speed goes very fast. Speed of sound sound goes very fast. Coming to liquid, as the distance is little far, So it takes some time to go from one particle to other particle. That's why the speed of sound is little smaller than solid. You see the gas? The particles are very far from each other. So it takes longer time to move from one particle to the other particle. It takes longer time to vibrate from one particle to the other particle. That's the reason why in solids, speed of sound is greater. But if you want to increase the speed of sound in gas, what you need to do? Just I have mentioned you need to increase the temperature. When you increase the temperature, the particle starts vibrating very fast. When the particle starts vibrating very fast, sound also travels very fast. In that way, you can increase the speed of sound here in the gas. Or else, in general, speed of sound is greater in solids. And if you see the order, in solid speed of sound is greater, and then liquid, and then gas. So gas speed of sound is less. Now we are going to discuss about the mathematics of sound. So that is nothing but properties of sound. 5 properties we are going to discuss: amplitude, loudness, wavelength, which is represented by symbol lambda, frequency represented by f, speed represented by v. These 5 properties we'll discuss now. Now see, on the board, a big wave has drawn. On y-axis I have taken pressure or density. Density symbol is rho. It's a Greek letter rho. Density. You can use the symbol small d also. Pressure or rho. On y-axis I have taken pressure, P naught maximum pressure minus P naught small less pressure or minimum pressure. O is the origin, and x-axis I have taken time. Okay, now see what happens. Amplitude. What is amplitude? Amplitude defined as, so I'm writing amplitude means it is the maximum displacement. Maximum displacement of the wave. Maximum displacement of the wave. That's the basic definition of amplitude. So this is for any wave you can take maximum displacement. Coming to sound, instead of displacement, I replace with pressure. So amplitude is the maximum pressure of the wave, or amplitude maximum density of the wave. Now see the wave here. So this is the amplitude. Maximum pressure of the wave, or maximum density of the wave, represented by A. Generally we use symbol A, but you can use any symbol you want. I can use P naught here, no problem. So amplitude is the maximum displacement of the wave, but for sound it is maximum pressure of the wave. Okay. Now, if we take SI unit, if it is displacement, the unit is meters. If it is pressure, the unit is pascals. Okay, that's the amplitude. Now, what is the significance of amplitude? The significance of amplitude depends on, or the significance of amplitude related to loudness. Loudness. See, some people speak soft voice. Some people speak with loud voice. Suppose if you look at me when watching this video, when I say sound, it's a soft sound. Sound, louder sound. So how do you differentiate soft sound, louder sound graphically? That is by using amplitude. More the amplitude means more the loudness. Lesser the amplitude means lesser the loudness. So loudness directly proportional to amplitude, or I can say the perfect mathematical relationship is the loudness I is directly proportional to square of the amplitude. I is also called intensity. Is one more physics word, intensity, or you can say loudness also. It's the square the amplitude. More the amplitude, more the loudness. Let me show you here. I will show you the soft sound and loud sound. using amplitude or the loudness also we can say. See, when I say soft sound, the pressure on a y-axis, time on x-axis. So when I say sound, soft sound, means the waves are like this. Small amplitude, see, this is very small amplitudes. Now if I say loud sound, it will be like this. You understand? See what is the amplitude now? See here. So here the amplitude is small, that's called soft sound. Here the amplitude is large, loud sound. Or you can say the small amplitude, it is less loudness. More amplitude, more loudness. Either the way you can say. So that's how the amplitude and loudness are related. Now next come to the property called wavelength. What is wavelength? Wavelength has got two definitions. One definition I'm going to tell you. Listen to me. So this is crest. This is compression. This is rarefaction. Compression, rarefaction. As I shown you earlier, the representation of compression, rarefaction with wave nature. Now, this is what called the wavelength lambda. This is also lambda. Now, how do we define? Wavelength is the distance between two consecutive compressions. Consecutive means next to next. Consecutive, next to next. Wavelength is the distance between two consecutive compressions, or it is the distance between two consecutive rarefactions. So how much distance is saying here, you have the same distance here also. So the definition you can see on the board, it is the distance between two consecutive compressions or two consecutive rarefactions. This is wavelength lambda. This is the correct definition. But sometimes you can show in this way also. See carefully. This is one wave. A, B, C. A, B, C. This C is not compression. C is a symbol here. A, B, C is a complete wave. When a wave travels a complete wave, then the distance traveled is also called wavelength. So this is also wavelength. Complete wave, wavelength. So the distance traveled by the wave, complete wave, wavelength. So the second definition also you can take. But this is the general definition, we agree. It is the distance between two consecutive compressions or consecutive rarefactions. Okay, that's good. Now what is the SI unit of wavelength? See the name itself, length. The length is nothing but distance. So the SI unit is meters. Okay. So the next one, frequency. What is frequency? Frequency tells the number of things done in a particular amount of time. Or the rate of amount of work is done in a particular amount of time. So generally frequency is the number of vibrations per second. Number of vibrations per second. Or number of oscillations per second. Number of rotations per second. So always frequency you are taking per second, per time. Okay. So let me write here. So the frequency is number of vibrations or waves per second. Now see this diagram once again. Suppose if I mention that this is one complete wave, C, D, E is one more complete wave. So two waves I have drawn here, A, B, C, C, D, E, two waves I have drawn. And to execute the two waves, the total time taken is 4 seconds. Imagine. So the two complete waves have executed in 4 seconds. Then in 1 second, how many waves are produced? Let me write. In 4 seconds, you produce two waves according to this diagram. So in 1 second, how many waves you can produce? So 1 by 4 into 2. how much you get? 1 by 2, which is 0.5 waves. So half wave, 0.5 is into half wave. That means in 1 second you can produce half wave. That is the frequency. So 0.5 waves per second or 0.5 cycles per second. See, this is a unit of frequency. 0.5 waves per second you can write. 0.5 cycles per second. What is cycle? Don't think this is a bicycle. In classical time, wave can also be represented, can also be called as cycle. See, A, B, C is one cycle. C, D, E is one cycle, two cycles. So waves per second or cycles per second. Or you can say one more unit which is very famous for frequency, that is actually SI unit of frequency. This is a Hertz. H-E-R-T-Z, Hertz. It's a scientist name. In short form, you can write Hz. So therefore, the value I can write F equals to 0.5 Hertz. Over. Instead of saying waves per second, cycles per second, I can simply say 0.5 Hertz. Okay, so this is how frequency is represented. Now, based on the frequency, you have two types of waves, high pitch and low pitch. What is the high pitch? The sound wave having high frequency is called high pitch. Let me show you graphically. See here. This is for 1 second only. See the number of waves. High frequency means more number of waves in 1 second. Now low pitch, see carefully. This is for 1 second. See here, so many number of waves are there in 1 second. There you have only 2 waves. 1, 2, 2 waves in 1 second. So time is same, but number of waves are different. More number of waves means more frequency. More frequency means high pitch. Less number of waves, low pitch, less frequency. You know, in general, on average if you take, in general, males have louder sound and low pitch. So we can speak loudly, but the pitch is less. Females have soft sound, but they have high pitch. High pitch sounds you cannot hear. If somebody screams, if somebody cries with high pitch, you can't. In movies also you can show, they will show you for the fun, like one person screams and when the person screams, the glasses break because of high pitch. Sometimes if you go into your kitchen room where you have different utensils, stainless steel utensils, and if you scream louder, then you can hear the resound effect in the kitchen because of the utensils, because you scream with high pitch. So high pitch is high frequency, low pitch is a low frequency. Now the last property, speed. In motion chapter we discussed the definition of speed. Speed is a distance by time. It is a distance by time. So here the distance is nothing but the wave travel distance. The wave travel distance in 1 second, and the travel distance is lambda. So I can write lambda. By time is t, capital T. Capital is a time period. Now v is lambda by t, or else you can write lambda by t as lambda into 1 by t. Both are the same. There is one more definition for frequency. Frequency is reciprocal of time period. Reciprocal means inverse. Frequency is a reciprocal of time period, means 1 divided by t. So instead of 1 by t, I can write f. So therefore v equals to lambda into f lambda. That is the formula for speed of sound. It's a very, very important formula. And you know the SI unit is just like a motion chapter we discussed. It is meters per second. For example, in this diagram, if I give the lambda value as say 220 meters, lambda value, and the frequency lambda is 220 meters and frequency is 3 hertz. What is the speed of sound? If I ask you, then simply apply the formula f lambda 3 into 220. The frequency is nothing but 660 meters per second. Absolutely, it is not in the air, because in the air we discussed is 340, 330, 340, 360. It is 660 meters per second. That means it may be a different type of medium. So just applying the two values, you can get the speed of sound. Okay, now we are going to some more concepts in the sound chapter. The first concept in reflection of sound. What is reflection of sound? The name itself tells you that reflection. How light comes, falls on the wall and bounces back. Similarly, the sound comes, falls on the wall or any substance, if it bounces back, it's called reflection. All waves satisfies law of reflection. It may be sound wave, it may be light wave, it may be any other type of electromagnetic wave. All waves have to, yes, they are satisfying the law of reflection. Now the question is, what is law of reflection? See the board. According to mathematics, we have drawn a perpendicular line to a surface. Say it is some surface, say it's a wooden surface, water surface, glass surface, any surface you can take. Okay, it is wood surface, glass surface, water surface, anything. And I have drawn a normal mathematically, which is perpendicular line. Now, a sound is produced at this point. Yes, is a source of sound. When the sound is produced, sound can travel in all directions. It can travel in all directions, but we are not interested to see all the directions. We will take only one direction. Let us say this is the direction of the sound and it falls like this. This line, like this. See, the sound waves are traveling towards the surface and they fall on the surface with an angle I. I is called incident angle. Incident angle. Let me write here. It is incident angle. When sound wave travels and falls on the surface with the angle I, it reflects. It reflects. And you can draw in this way, reflected wave. This is called reflected wave. And this reflected wave make an angle R with the normal. R is called reflected angle. Reflected angle. Now, law of reflection says angle I is equals to angle R. This is the law of reflection. If the sound wave travels and falls with the angle of incidence 30 degrees, it will reflect with the angle 30 degrees. If it falls with the incident angle 60 degrees, it will reflect with the angle 60 degrees. It is true. Because all the waves wants to travel to a distance as short as possible. As short as possible. And mathematically we found that with what angle they incident, with the same angle they reflect, and that will be the shortest distance for it. That's why law of reflection says angle of incidence equal to angle of reflection. Now sound, when it falls on the different substances, it reflects. Sometimes it has a regular reflection, sometimes it has irregular reflection. How it is possible? If you have soft surface, polished soft surface, a soft wooden surface, and sound comes and falls on the surface, then it has a regular reflection. If it has a rough surface, then it has irregular reflection. Let me show you here. See, this is one surface, wooden surface, which is soft one. When the sound wave comes like this, incident on the soft surface, it reflects regularly. But if it has irregular surface, then the sound wave falls incident and it reflects irregularly. irregularly. Irregularly means in different directions. One more thing. In auditoriums, big auditoriums like in Hyderabad, Shilpakala Vedika auditorium, if you see, it's very big auditorium, many times, many functions happens in that auditorium. So, if the people start speaking on the stage or some dance is happening, some person is singing a song, that has to be heard by all the audience sitting or standing in the auditorium clearly. Then how it is possible? They can't take mic and keep big sound boxes in front of the audience. They start singing a song. Maybe that is, they think that it should be a pleasant sound, but maybe it become noisy for them. That's what they do. They keep systematically some sound speakers corners of the room, so that these speakers synchronized and give a pleasant sound to the people. Sometimes what they do, instead of keeping the speakers, of course they use speakers, sometimes they use some special type of speakers, a special shaped speakers, it's called concave shaped, like this, see, like this, concave shape, ellipsoid shape we say. So what happens when the sound from the source goes and falls here and it reflects in all the directions. See here, now what happens? So the concave shaped speakers advantage is that it covers wider area. So when there's a big room, the sound spreads in all the directions, so that the sound can be in a wider area. The better example for you, dish antennas, Tata Sky, DTH. If you see the dish antennas, the dish is in the ellipsoid shape, so that the rays falling on it, they spread in all the directions. In the other way, the different rays falling in different directions should be concentrated to one point. In that way, these type of shapes are used for spreading the waves in all the directions, or take the waves in all the directions and focusing to one point. So using this type of shape, sound can be spread in all the directions. That's how you can reflect the sound. There's one more major thing in reflection of sound we should learn, and that is echoes. So, as I mentioned you, echo is a very, very important concept in the reflection of sounds. When you go to an open area, suppose think that you have gone to a hill station and you're standing on the high peak and you have shouted. Suppose think that in front of you, long distance, you have mountains, and when you shout loudly, within seconds you can hear your sound again. One more example. You have gone to an auditorium which is empty, nothing is in the room, it's a big room, nothing is there, and you shouted. Then you can hear the sound again and again. And generally we say this is a reflection of sound. Yes, it's a reflection of sound, but it's a special case of reflection of sound which is called echo. So the definition of echo is very simple, it's a reflection of sound. But how you get your sound again and again, how it is possible? Yeah, let me explain you. See the example here. There is a car at rest state blowing the horn, and that horn is nothing but sound. The sound travels towards the peak and reflects. When the car blows the horn, the sound goes towards the peak and reflects. So the total distance traveled is d plus d, 2d. Suppose think that in time t seconds, the car driver heard the sound again and again, which is the echo time. Then according to the formula, speed equal to distance by time, right? Speed equals to distance by time. Now, if I write distance d, I'm not correct, because we are taking d means only one wave distance, but here you need to consider the first wave and reflected wave both. So d plus d which is 2d by the time taken is t. So therefore v equal to 2d by t implies d equals to vt by 2. So this is the formula for finding minimum distance to produce echo. So what I want to tell you that in this room, if I shout, you can't hear any echo. See, I'm shouting. My voice is raised, but you can't hear echo. That means it is not possible to produce echo in all situations. There are some conditions. Then only you can produce echo. That's why when the beginning of this echo, I have told you that you are at the peak in front of longer distances. You have mountain. Then you shout, you can hear the echo. You have gone to auditorium, which is empty, big room. If you shout, you can hear the echo. So these are some conditions. So mathematically, what is the minimum distance required to produce an echo? See here, d equal to vt by 2. Now, speed of sound, let us take 330 meters per second. Time. See, this time is experimentally found. The scientists have done experiments. And they found that the time for producing echo is 0.1 second. 0.1 second. Minimum time, 0.1 second. Then d equals to 330 into 0.1 by 2. So how much this is? This is 33 by 2, which is 16.5 meters. So the minimum distance between you, or means between the source and the peak, means the reflector, should be 16.5 or more than 16.5. If it is less than 16.5, you can't produce echo. That's why here I'm standing, I'm talking to you, but I'm unable to produce echo because between me and the wall, the distance is not 16.5, less than 16.5. But in the open areas and in the auditoriums, the distance is very far, very big. That's why when you shout, when you scream, you can hear the sound again and again. In this problem, if you see 330 meters per second I have taken, that's why I got 16.5. But sometimes textbook shows 17 meters also. That is also correct. But that is correct when you take V is 340 meters per second. Okay. So we have considered that minimum distance is 16.5 meters. Now let us do numerical. See here. There is a peak. The car produces a sound, blows the horn. After 4 seconds, he heard the echo. Now you need to calculate what is the distance between the car and the echo. So quickly write the formula, d equal to vt by 2, v is 330, time is 4 by 2. So 2 2 is 4, so this is nothing but 660 meters. So that's how you can calculate the distances. Using this echo concept, we have many applications. The main application of echo is sonar. And maybe you heard about this word sonar. Sound navigation and ranging. The sonar technique used in the ships. When the ship is sailing on the water and the ship wants to find out any submarine under the water, enemy submarine is sailing, or any animals, sea animals which are harmful to the people or inside the sea, or any treasure if they want to find, of any city they want to find, they can use sonar technique. So sonar technique works based on echo concept. See the board here. There is a ship, it's sailing on the water. Under the water you have a treasure. So generally what they do, using sonar machine, they send the waves. These waves travel into the water and reflects back. And what they do, with the time of echo, the time of reflection, they usually find that what is the distance between the ship and treasure. In other words, what is the depth of the sea, how far the treasure from the ship. In this way they will do the necessary action. So d plus d, 2d, v is the speed of sound, by time is the t is the time taken. The same formula, v equal to 2d by t, implies the distance traveled d equals to vt by 2. So earlier what the formula I have derived, same formula you can use. But generally, in sonar, they don't use the waves what I am producing, what you are producing. They use special type of waves, and those waves are called ultrasonics. Ultrasonics. Ultrasonic waves, a special type of waves. I will explain you within a few moments. So they send ultrasonic waves, and ultrasonic waves speed, say it is 1500 meters per second in the water. Suppose in this example take t equals to 5 seconds. Then what is the depth of the sea? D equals to Vt by 2, 1500 into time 5 by 2. So 2.5. So simplify 0, 0, 15, 5, 75, 5, 7, 37. So the answer is 3750 meters. So that is how the machine calculates. Actually, this is the mathematics we're using in calculating on the board, but the machine has programmed so that automatically calculates and shows the distance. You can produce sound, I can produce sound, and you can hear different types of sounds. But is it true that we can hear all types of sounds? No, it is not true. Is it true that the animals, what type of sound they can hear, we can also hear the same type of sounds? It is also not true. We can hear a certain range of sounds only, and that range basically based on frequency, and that range is called audible range. So if the sound frequency is 20 Hz to 20,000 Hz, yes, is audible range, means the range of frequency we can produce and we can hear. Less than 20 Hz, you can't hear. More than 20,000 Hz, also can't hear. So as human beings, we can produce up to this limit, up to this range, 20 Hz to 20,000 Hz. It's called audible range. Now, the sound waves which are less than 20 Hz are called infrasonics. Which are more than 20,000 Hz are called ultrasonics. Infrasonics have very less applications, but ultrasonics have wider applications. Earlier, I have actually explained you about uses of ultrasonics in the concept called sonar. There are more applications of ultrasonics. One is cleaning capillary tubes. Cleaning capillary tubes. Capillary tubes means those are glass tubes whose area of cross section is very, very small. Area of cross section is some range of millimeters and micrometers. Micrometer means the thin of your hair. Those are tubes, but size is thin of hair. That means you cannot send the water inside. This much of thickness of tube, how can you send the water? How can you clean? So that is possible by ultrasonics. They will send the ultrasonic wave through the tube, and those ultrasonic waves goes and clean the tube. And you know the best example nowadays, water purification. Water purification has done in many ways, and one way is ultrasonic purification of water. And one more application, sonar, actually we discussed, is used for finding the depth of the sea and find the treasures under the sea water. Echocardiogram. They send the ultrasonic waves into your body, parts of the body. They fall on the parts of the body, reflect back and create an image on the computer screen. Generally, this is used for knowing the functionality of your heart. That's called echocardiogram or echocardiography also. One more application, detection of stones in kidneys and gallbladder is a very, very advantage. In the kidneys we have stones. How do we know the kidneys have stones? How many stones we have? Or in gallbladder. Similar technique. They will send the ultrasonic waves and it goes into the kidneys and reflects back from the stones and show the stones on the computer screen. Nowadays, the technology is developed. You can use ultrasonic waves, but technology developed using light waves. Laser light. The laser rays goes inside. They're not only showing the kidneys, they are used for removing the kidneys also. Actually, the laser light goes into the stone and they burn the stone. They remove the stone completely. So today the technology developed, we have laser techniques which are advanced than ultrasonics. The last application, detection of flaws in pillar constructions. A big bridge is constructed. The bridge is supported by big pillars, like in Hyderabad Metro Rail project. The big pillars are supporting the bridges. Now, if you see the pillar, from outside the pillar is very strong, very big and very strong. It is only correct when the pillar is completely solid inside also, completely filled with matter, mass inside. Sometimes what happens, they are constructing, some spaces are not filled inside the pillar, like this. This is the pillar, maybe some places the mass is not filled, and outside you can't see because it is polished. But how do you know that whether the gaps there or not? If the gaps are there, it's very dangerous. On the bridge, if any car goes, heavyweight car, heavyweight truck goes for a long time, that will damage the pillar because of the gaps. So to detect the gaps, they will send the ultrasonic waves on the pillar. So the ultrasonic waves goes and enter into the hole and reflects back and tells that what is the size of the hole inside the pillar. Then they will repair. They will make sure that those holes are filled with the mass. So that's how you have many applications of ultrasonic waves. So far we discussed about the sound, the properties of sound, wave nature of sound, speed of sound V equal to F lambda. Then we discussed about reflection of sound, echo, ultrasonics, infrasonics and ultrasonics applications. Now it is a time to apply our knowledge to solve problems. So here is the first problem for you. Flash and thunder are produced simultaneously, but thunder is heard a few seconds after the flash has seen. Why? Flash is nothing but light. Thunder, it's sound. Light speed in air. What is the value of light speed in air? If you recall it, it is 3 into 10 power 8 meters per second. Means in 1 second, it can travel 3 lakhs kilometers. If you see the sound speed in air, it is only 330 meters per second. Light speed is the maximum speed in the universe. So far we know about physics of universe. Maximum speed. It is 3 lakhs kilometers per second. In 1 second it can travel 3 lakhs kilometers, but it can travel only 330 meters. That's the reason why you can see the light first and later you can hear the sound. Second problem for you. Audible range is 20 Hz to 20,000 Hz. You need to calculate typical wavelengths at that frequencies or typical wavelength range for that audible range and take speed of sound 340 meters per second. So how do we find this? Speed, you know, least frequency, you know, maximum frequency, you know, you need to find wavelength. You know the formula V equals to F lambda. Okay, but I want wavelength, so lambda equals to V by F. This is the formula you need to use. So for the frequency, least frequency 20 Hz, the lambda 1 equals to V is 340, frequency is 20. So the answer is 17 meters. Okay. Now F2, the highest frequency range, 20,000 Hz. The wavelength lambda 340 divided by 20,000. Now 0 0 cancel. How much you get? 17 by 1000. This is nothing but 0.017 meters. So that's how simply using this formula you can get the two values. One more problem for you. Frequency is 100 Hz. How many times does it vibrate in 1 minute? 100 Hz is nothing but 100 vibrations per second. As I told you in the earlier class, 100 vibrations per second, 100 cycles per second, 100 waves per second, everything is correct. And here the question is, in 1 minute, how many times it vibrate? So you can start like this. In 1 second, it vibrates 100 times. In 1 minute, 1 minute means 60 seconds, how many times it vibrate? So 60 by 1 into 100. So this is nothing but 6,000 vibrations in 1 minute. So one more challenging problem for you. There is a tower of height 500 meters. At the bottom of the tower you have a pond. A stone is dropped and stone falls on the pond and produces the sound. Now the question is, how long it takes to produce the sound, or how long it takes to hear the sound produced by the pond. So you're asked to find time taken to hear the sound. Okay, now how do we calculate? If you see this picture, the stone has to travel from here to here. Some time will be taken. Let us say the time is t1. After stone falls in the pond, the waves are produced and the waves travels to the height to this point. Then the person who is standing here, can hear the sound. So this time is t2. So t1 plus t2 is the total time. So say total capital T, if I take capital T equals to t1 plus t2, this is equation 1. Now first we find the t1. As the stone is dropped freely, its initial velocity u equal to 0. t1 is the time taken, height is given, as falling down, acceleration a equal to plus g. So therefore you can use the formula s equal to ut plus half at square. Now height is 500 equals to 0 plus c, half into g. G is 10. So half into 10 is 5 t square. Let me write t1 square. So therefore 5t1 square equal to 500, and t1 square is 100, implies t equals to plus or minus 10. We take positive number, which is 10 seconds. You got t1 10 seconds. Now it means the stone is on the pond, surface of the pond. Now it flashed the sound. When it splashed the sound has to travel to that point. So we need to take now speed of the sound. Speed of the sound is 340 meters per second, and you know the speed equal to distance by time. I want time, which is distance by speed. Let me write t2. So the distance traveled is 500 meters and speed of sound is 340. And if you simplify this 300 by 340, you will get 1.47 seconds. So therefore the total time t equals to 10 seconds plus 1.47, which is nothing but 11.47 seconds. So it takes 11.47 seconds time to hear the sound produced by the surface of water in the pond. So one more problem for you. Sound wave travels at a speed of 339 meters per second. If its wavelength is 1.5 meter, what is the frequency of the wave? So you know the formula v equal to f lambda, therefore frequency f equals to v by lambda. So speed is 339, the lambda is 1.5. So if you simplify this, you get the answer 226 Hertz. It's a direct substitution problem. One more problem for you. There's a ship on the surface of the sea, water, and through the ship, the sonar machine used and sent the waves, and the sonar produced an echo at time 5 seconds, and distance between the point under the sea water to the ship is 3625 meters. Now the question is, calculate speed of the sound. So by seeing this diagram, you can recall that it is based on echo, and the echo formula is d equals to vt by 2. But our interest to find speed of the sound, you just change the formula, v equal to 2d by t. Now 2 into distance is 3625 by 5 seconds. Then if you simplify this, you will get 1450 meters per second. So this is the speed of the sound in water.